Now that we've developed four exponent laws of the real number system, we often need to use them in tandem to simplify more complicated expressions, such as these here. So let's go through again. You may need to use multiple exponent laws to simplify each of these. First, we've got this big product raised to a power. Anytime you have a product raised to a power, right, this is -4 times x cubed times y to the fifth, the exponent is applied to each of the factors. So we have -4 needs to be squared, and again, this is not the square of -4, this is the square of -4. We need to square the x cubed, and we need to square the y to the fifth. And now, of course, -4 times -4 is 16. But whenever you raise a power to a power, that exponent law says that we need to multiply the two exponents. And we get x to the 6th power here and y to the 10th power. This is the simplified version of this expression right here. And we use two of the laws to get there. Let's take a look at this one. In this case, we've got a fraction raised to a power. And one of the exponent laws tells us that if we've got a fraction raised to a power, we raise the numerator to the power and the denominator to the power. But now, this top, we've got a product here raised to a power. So that means we need to raise each factor to the power. The 2 gets raised to the 3rd power, and the x gets raised to the 3rd power. So you got 2 to the 3rd power times x to the 3rd power over y cubed. And then, of course, don't leave 2 to the 3rd power. You can evaluate that. 2 times 2 times 2 is 8. So we have 8 times x cubed over y cubed. This is equivalent to the original expression up here. Let's try this last one. Here we have the product of -7y to the 5th times 3y squared times 2y. Don't forget that there is a multiplication going on between each of the numbers and the corresponding variable quantity. So we have one big product here, and we can do multiplication in any order. So we've got -7 times the 3 times the 2 will give you -42. And then we've still got y to the 5th times y squared times y. Well, of course, we can simplify this. First of all, what's the exponent here on y? Well, if it's not written, that's simply a 1. We saw in one of our previous exponent laws, when you multiply exponential forms with the same base, you add the exponents. So we've got -42 times y to the 5 plus 2 plus 1 gives us y to the 8th power. This expression is equivalent to the original one, and it's much simpler than it originally was. So this expression is equivalent to this one, this expression is equivalent to this one, and this expression right here is equivalent to this one. Our exponent laws are used to simplify expressions, and often we need to use more than one exponent law to simplify any one expression. Now we need to deal with simplifying fractions, so something like this, or this, or this. Technically, the four exponent laws that we came up with, none of them apply to these three. And there is an exponent law that does apply to simplifying fractions like these, but it can produce negative exponents. And while negative exponents are legitimately defined in the real number system, they are not part of our course. So we are not going to use negative exponents. So I'm not even going to mention what the law is itself. Instead, we're going to look at a practical way of simplifying each of these expressions. And notice we're going to do it in very much the same way that we developed all four of the exponent laws that we looked at. We're going to first expand the expression. Let's take a look at this fraction here. First, I would suggest just simplifying the numeric part. 10 over -25 simplifies to 2 over -5, because 5 goes evenly into both 10 and -25. There's another way to look at that, but that's sufficient for us. So my suggestion is first to simplify the numeric part, and then we're going to expand the rest. P cubed means P times P times P, Q squared means Q times Q, and P on the bottom, and Q cubed means Q times Q times Q. Once you've expanded it, we now want to divide out the common factors. In general, if you've got A times B over A times C, that's the same thing as B over C, so long as A is not 0, because otherwise you would not be able to do the division. We can divide out common factors. A divided by A is 1, and then 1 times B is still just B over here. So let's divide out the common factors over here in this expression. First, we have a P in the top and a P in the bottom, so P divided by P is 1. There's not an additional P in the bottom, so these P's up here in the top are going to stay here. And then there's a pair of Q's we can divide out. We get, of course, 1. Q divided by Q is 1, so long as Q is not 0. And then Q divided by Q again is also 1. And there's nothing else in the top to divide out with this 1Q here. So once we've divided out the common factors, we want to write what we have left in exponential form. In the top, we have 2 times 1 times p times p times 1 times 1. Of course, multiplying by 1 doesn't do anything, so we can kind of ignore those. We've got 2 times p is the same thing as 2 times p to the second power. Over in the bottom, we've got negative 5 times q left. Negative 5 times q is negative 5q. This is an equivalent expression to this one, and it's much, much simpler. Also, again, under the assumption that p and q are not 0, otherwise we couldn't have done these divisions. So let's simplify this next expression. Here, there's no numeric term to simplify, so let's just start expanding right away. X squared is xx, y cubed is y, and in the bottom, x times y squared is x times y. Again, we want to divide out the common factors. Notice that we have a pair of x's here we can divide out, a pair of y's, and another pair of y's that we can divide out. Now, I didn't even write it in, but you certainly can. X divided by x is 1, y divided by y is 1, y divided by y is 1. And the reason I didn't write it in is because when I go to rewrite this top expression, the multiplying by 1 won't actually change it. So all we have left in the top here is x times y. We've got xy, and notice in the bottom, we're not left with anything. So x times y is our simplified expression. This is equivalent to this one, but much, much simpler. Let's try this last one. Again, there's no numeric factors, so we'll go right to expanding. X times y squared is x times y. X squared is xx, y cubed is y. We'll divide out the common factors again. We can divide out a pair of x's, we can divide out a pair of y's, and another pair of y's. Notice all the variable factors in the numerator are gone, and we still have an xy in the denominator. However, our answer is not xy. Up here, our final answer was xy because you had x and y in the top, and everything divided out in the bottom. Over here, you've got xy in the bottom, but that doesn't mean suddenly we don't have a fraction anymore. Technically, we need to pay attention to the ones here. X divided by x is 1, y divided by y is 1, y divided by y is 1. So we still technically have 1 in the top. So this does not become xy, it's 1 over xy. Big difference. And this should make some sense that this is equivalent to this because these two are reciprocals of one another. So these two expressions should be reciprocals of one another, in which they are. Let's now look at two radical laws that are technically exponent laws in disguise. First, a square root is an example of a radical. So a lot of people read, instead of square root of 5, they might actually call this radical 5. Right? So it's a specific type of radical. So we want to be able to simplify expressions like this. Square root of a times square root of b, or square root of a times b, that quantity. Square root of a divided by square root of b, or the square root of the fraction a over b. And technically, I've got it really tiny here. The radical laws are actually exponent laws in disguise. These laws are functions of the previous exponent laws that we already looked at. However, I'm not going to explain that at this moment because it requires a knowledge of fractional exponents. And fractional exponents are a concept that is outside of our course. So instead, this is a rare moment where I'm actually going to just give you the laws rather than explain where they come from. So square root of a times the square root of b is the same thing as the square root of the product of a times b. Equivalently, you can take an expression and write it like this, or you can take this expression and write it like that. That's always true with equality. This thing equals this thing equals this. But I'm just going to write it again over here just to make sure it's clear. So you can take the square root of the product and break it into the product of the square roots. So really, this and this are the exact same thing. This is a redundancy of this, but just to make sure it's clear that sometimes you might want to take this and write it like this, but you also might want to take this and write it like this. They're equivalent. Now, when you have a quotient of radicals, that's the same thing as the radical of the quotient. So we can rewrite that as the square root of the fraction a over b. Or said differently, if you went the other way, if you have the square root of a fraction, you can rewrite that as the square root of the numerator divided by the square root of the denominator. Again, this equality right here is saying the exact same thing as this equality. It's just written again just to make sure you realize that you can go from this to this, or you can go from this to this. So ultimately, there are two radical laws here, this and this. These are, again, just another way of writing each of these. Now, before we do some examples with this, let's make sure it's clear. Again, just like the exponent laws, again, really the radical laws actually are part of the exponent laws. The radical laws only apply to products and quotients. Notice we have a product here and we have a quotient here. It does not apply to sums and differences. So for example, you could not take the square root of the sum of 9 and 16 and break that up into the square root of 9 and the square root of 16. Because for example, technically 9 plus 16 is 25, and square root of 25 is 5. But over here, square root of 9 is 3, square root of 16 is 4, 3 plus 4 is 7. Those clearly are not equal to each other. All right, so the radical laws, just like the exponent laws, apply only to products and quotients, not to sums and differences. Let's now take a look at a couple of examples where we can apply these radical laws. We want to simplify each of the following radical expressions. This one, and this one. Now, if you were to plug square root of 2 into your calculator, get an approximation, it would give you 1.4 blah, 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 blah. Square root of 50, you would also get a decimal approximation. And if you multiplied the two, you'd get a new decimal approximation. But in general, we don't want a decimal approximation if it's possibly avoidable. So let's see if we can apply the radical laws to rewrite this first and get something that's not a decimal. It's not always going to be the case, but with these examples here, it will work. So the radical laws basically told us that if you've got a product of a square root, you can rewrite that as the square root of the product. So the square root of 2 times 50. We can recombine those. And of course, 2 times 50 is 100. And the beauty of doing this is 100 is a perfect square. So when we take the square root of that, we get just the integer 10. So this expression is the same as that. I'd much rather look at 10 than the square root of 2 times the square root of 50. Over here with this one, the quotient of the radicals can be rewritten as the radical of the quotient. We can recombine it like this. And the beauty here again, 50 divided by 2 is 25, and 25 is a perfect square. So the square root of 25 is exactly the integer 5. 5 is equivalent to that. I'd much rather look at this than that. And finally here we have the square root of a fraction. Now, a lot of people wouldn't be comfortable thinking about what fraction can I multiply by itself to give me back 9/25. That's the idea of a square root. So instead, let's apply the radical laws. If you've got the square root of a quotient, you can break that back up into the square root of the numerator divided by the square root of the denominator. And now the square root of 9 is 3, and the square root of 25 is 5. So this expression, radical 9/25, is the same thing as 3/5. This is much easier to deal with than that is, but they're the same exact thing. So with one final note here, to make it clear that with an inequality, you can go either way. You can change A to B as if A is equal to B, or you can change B to A if A is equal to B. And notice that these last two demonstrate that. Here, we had a quotient of radicals, and over here, we had a radical of a quotient, and yet both we were able to rewrite. Here, this we recombined to get this. This one, we broke it apart to get this. So sometimes you may want to go in one direction with inequality or go in the opposite direction. Either way, we've got much simpler expressions here instead of these.